morning, guys. Today we're going to start putting together all this sequence series stuff into some applications. We're going to do finance applications. Something I really enjoy getting to play around with, doing all the calculations with different ways we can use money or add up money, because that's all a series is, right? We're adding up a pattern set of numbers again and again and again. So in this first example, it says we have a job that pays a salary of $25,000 the first year. For the next 19 years, the salary increases by 5% each year. What's the total amount of money earned over the 20 years? So we're saying if we added up the salary for this specific job every single year, what would we have? How much would we have earned after 20 years? So the question is really saying, what's the sum of 20 years of this specific sequence? Well, in year one, we had $25,000. In year two, we had $25,000. The previous years, with the additional 5% added in. Well, the way we add 5% in is to multiply by 105%, because we have the 100% we originally had plus the additional 5%. So that's why we have times 1.05. Well, to get year three, I take the previous year times another 105%, and then we continue that pattern. So as we see, we're multiplying by 1.05 or 105% every single year. Well, if we're multiplying by the same value again and again and again, we know that we have a geometric sequence. So the 20th year, just put our explicit formula for a geometric sequence in there. So remember, explicit formula says A1 times the rate to n minus 1. So the 20th year would be 25,000 times 1.05 to 20 minus 1. Now, we could sit there and calculate these 20 different values and add them all up, but as we've talked before, we have these formulas for the sums of these series, what we get when we add all of them together at one time. And so I want y'all working with those instead of doing the trivial calculate and add stuff. Let's use these formulas. So I recognize it's geometric. We were multiplying by the same value every time. And it was finite. It was a fixed number of years, a 20-year span. So we have the formula for the sum of a finite geometric was A1 times 1 minus r to the n all over 1 minus r. Let me just plug in our numbers. A1 is 25,000 as our initial term, our initial term. R was the rate we grew every single year in this case, so 105% of the previous year, executed for 20 years. And then we're going to punch all that into a calculator and see what it gives us for the sum. So I want you guys to pause the lecture real quick, type that in, because I want to. That's probably the hardest part on all of these is figuring out how to get it actually calculated, because we have so many exponents and fractions and binomials and things like that. So pause the lecture for just a quick second, key that in, and we'll see if you actually keyed it in correctly, and I'll show you what the answer should be. Okay, hopefully you were able to get $826,648.85. So $826,648.85. The way you go about keying that in is you can go one of two routes. I can start on the inside and work my way out. So I can type in 1.05 to the 20th, get that number, 1 minus that, get that number, so, multiply it by 25,000. Get that number and then divide it by 1 minus 1.05. If you don't want to do that and you want to key it all at once, just remember, group your numerator together, group your denominator together, and you should be able to key in your calculator just like that to produce that value right there. So it's really just taking the same things we've been doing with series, but instead of saying evaluate this series, it's giving you, it's kind of writing out a verbal description of what the series is, and we've got to figure out the series, then use the appropriate sum formula. So that's one example. There's 3 other examples we're going to cover in this little lecture. And the next one deals with multiplier effect, which is very similar to this, except we're not dealing with exponential growth. It's an exponential decay type of sum. But give me a second, I'll get that multiplier effect problem up here for you. So here we have our next example. This one's a multiplier effect. That's what I've seen it described as. Of course, all these were multiplying by something, but for some reason this one has been specifically called a multiplier effect problem. So that's what I'm going to refer to it as. This one says a new factory in a small town has an annual payroll of $6 million. Traditionally, the members of this town spend 60% of their incomes in the town within the year. What is the total economic impact of the factory on the town each year? So what we're trying to say is, yeah, the factory is paying out $6 million in salaries, but people are then spending that money in the town, in this case 60% of it, and then if they're spending 60% of that income in the town, then the people in the town that they give their 60% of the $6 million to are also then going to take 60% of that and spend it inside the town. And then that group is going to take 60% of what they just received and spend it inside the town. So what we get is, on that first round of spending off the $6 million, 60% of it gets spent. So that's how much was spent inside the town off the first go around. Now, this amount of money was spent inside the town. Well, we're going to take 60% of that and then spend it back inside the town. So the second round of spending. And then the next round, the third round of spending, we would take 60% of this and spend it in the town. So we're using the money again and again and again and again and again. So while it started out as $6 million, it's actually getting used, changing hands so many times, it's going to be worth more than $6 million by the time everybody has finished spending their 60% of that. So what we're getting is this infinite geometric. We're multiplying by 60% every single time. Multiplying by 60% again and again and again and again. So, and we're going to go through that until it's completely whittled down and there's no money left out of that original $6 million. The reason we know it's infinite, because again it's going to keep going, because it's whittling down. It's a smaller number. Remember, we get to use infinite geometric if A1 is less than, or absolute, not A1, if the absolute value of R is less than 1, which in this case it is because it's 0.6. So if our values are getting smaller and smaller and smaller, geometrically smaller, then we can use this infinite geometric sum, which is what we have. So remember your formula, A1, which is the initial amount. The initial amount on this one's different from the last one though. It's not the $6 million. They didn't spend $6 million the first time, because we're trying to figure out how much money total was spent from that $6 million in the town. So the initial amount spent was 60% of the $6 million. So that's why our A1 is 60% of the $6 million. And then you do 1 over 1 minus R, so 1 minus our common ratio, which is spending an additional 60% every single time. When you go through and punch that in, remember parentheses, numerator, parentheses, the denominator, you're going to get $9 million total from that $6 million. So while it started out as $6 million being paid to the workers, the town actually exchanged $9 million worth of goods and services from that $6 million. So here we have our third example. Third example says, to save for retirement, you decide to invest $2,500 into an IRA at the end of each year for the next 25 years. IRA is an individual retirement account. It's a way to save up money and get money back as you do it. If the annual rate of return is 9% and compounded annually, find the value of the IRA after 40 years. Now, there's a little bit more involved that goes here. It's kind of some real simplistic numbers to make the computation easy, but we'll get the general idea behind what's going on from this example. But the idea is you give somebody money and they pay you for it. That's what interest is. So they're paying you to let them use your money. And in this specific problem, it averages out to about 9% each year over the 40 years. So we want to figure out what we're going to have after these 40 years. Now, this is very similar to a compound interest problem that we did earlier in the year. But that problem was I invest one amount one time and then I leave it alone. And the interest gets added in again and again and again. This one's different in the fact that whereas investing an amount of money, that's going to get interest put on it. Then we're going to invest the same amount of money again, and then we'll get interest put on that new total. Then we'll invest the same amount of money again, and we'll get interest put onto that total. So we get kind of this compounding by multiplying by the same number again and again, a geometric, plus we're adding the same amount of money in every time. So it's kind of a mashup, finding the sum when we have an arithmetic and a geometric all going on at the same time. So what we use is this annuity formula. Annuity means we're annually adding a certain amount of money in. So the annuity formula says that the balance after T years, that's what A represents, is going to be our payments. So where it says periodic payment, the period just kind of needs to match up with the N, the frequency of compounding. So if we are compounding annually, the payments for what we're doing would be done annually. If we were compounding monthly, then the payments would be monthly and things along those lines. So it's the periodic payments, how much we're putting in. And in this case, it's $2,500 once a year. R is our annual interest rate, which is same R that we used before, and T is the number of years of investment. So if this is our formula, A equals P over R over N times 1 plus R over N to the N T minus 1, we can see all those little elements of the geometric and just that regular compound interest formula. There's our pieces from our compound interest formula. And so we get to see all the little pieces of geometrics and arithmetics all kind of crammed into one formula. So in this specific problem, they said we want to know how much is there after 40 years. So they're looking for the balance of the account. So we're just going to plug in our payment, $2,500 per year. Interest rate is 0.09 over 1. And then, again, R over N, 0.09 over 1, raised to the 1 and 40. N is 1 because it says we're compounding annually. That's one time a year. If it had said quarterly, N would have been 4 in that case. So we go through, do all the calculations. This one I'll calculate a little bit differently than the other ones where I just typed it all in at one time. This one and the next one, what I'll do is I'll start on the inside and work my way out. I'll figure out my R over N. I'll add 1 to that. I'll raise that to the N times T. I'll then subtract 1 and multiply by this, then divide by this. So I'll just start on the inside and work my way out using that second answer function on the calculator just to keep me from having an error with parentheses or something along those lines. When we do all that, what we find is we're going to have a balance of $844,706.11, which is very interesting because if you think about how much did we put in over a 40-year span. Oh, I don't know why I have 25 years right there. It should have been 40 years. Bet y'all were wondering what was going on there. Let's make that 40 years. Okay, so value after 40 years, that should have been 40 years, not 25 years. Okay, so after the 40 years of executing this, we took $2,500 for 40 years. If you were to just real quick punch that in, what's 2,500 times 40? And you should see that it's $100,000. So by simply investing $100,000, by parting with $2,500 a year, we have, after 40 years, $844,000, almost $850,000. So we're getting almost a, 750% return on investment just by parting with, again, $2,500 a year. So it's kind of this one I like because it really shows the power of compounding, and especially getting in there and doing it early. Because if you were to recalculate this, and something that we'll look at in class, recalculate this same thing with different amount of years and see how drastically that changes. And play around with these different numbers and see what kind of impact. Because again, we're talking about exponentiation and compounding, and it's a very powerful force mathematically, the way these numbers can grow very quickly. Now this specific formula can be used for a number of problems. They could say, I want a certain amount. What interest rate do I need to get? How many years do I need to wait? What specific payment do I need to make for a certain number of years to get a specific amount? So there's a lot of flexibility in this formula, a lot of things that we could be solving for. So this is the basis of the formula, and then when we get in class tomorrow, we'll explore kind of different questions we can ask with this annuity formula. All right, one last formula which deals with loan repayment. Give me a second, I'll get that one up here for you. Here we have the last example I want to look at in our applications of series problems. And this deals with loan repayment. You can afford a $250 per month car payment if the annual interest rate of a 5-year car loan is 6% compounded monthly. How much money are you able to borrow? So if I can afford to pay $250 a month, how much money can I actually get for $250 a month is really what this question is asking. Now if we were to do the math on $250 a month, $250 a month for 5 years comes out to $15,000. So it's really what the question is saying is if I can afford to give you $15,000 over this 5-year span, how much money can I get up front? So it's a losing proposition for us, but this is a very, very important problem, especially with what y'all got coming up with buying cars, buying houses, paying back student loans, and all the good things that come with becoming a grown-up. So let's look at how we would attack this specific problem. We have this loan repayment formula. Loan repayment formula says if I borrowed this amount, and P is my payment each month, if we're talking about monthly payments, then the R's and N's and T's mean the same thing they did on the last one. So A is how much we borrowed. It was our initial amount of the loan. And P is the payments. It's how much we're investing or how much we're putting in each period. So in what we're doing, it's going to be monthly payments. R is still your annual interest rate. N is the number of times compounded per year. And T is the number of years that we're going to be paying on this loan. From there, it's just real simple. Put the numbers into the formula. So payment of $250 per month, so $250. Interest rate is 6%, compounded monthly, so that's 12 times per year. Again, 6% interest, 12 times per year, 12 times per year for 5 years. Go through and just like on the last one, what I would do if I'm typing this in, I'm going to type in 0.06 over 12. Get that answer and then hit +1. Get that answer and then raise it to 60. 12 times 5 is 60. Get that answer. And then I'll do 1 divided by that value. Then I'll do 1 minus that value. Then I'll do that value times 250. And then that whole value divided by 0.06 over 12. So start on the inside, work your way out. And you should get to the $12,931.39. So we're really trading $15,000 over a 5-year stretch to get a $12,931 car right now. So that's how the loan repayment formula works out. This one's not a bad trade-off because inflation would probably eat up close to that over 5 years anyway. So and this one is not a bad trade-off. We'll look at some problems in class that deal with looking at houses and things like that, student loans over a longer period of time than 5 years. So we'll get to see kind of that big impact of compounding and those interest payments over those long periods of time. But this formula, it's not necessarily about you paying in and trying to decrease, because what's going on is you're paying towards something, but the goalpost is constantly moving. How much you owe is constantly moving because they're adding interest onto that every time. So while you're paying it down, they're adding more on, and then you'll pay it down and they'll add more on. So that's why it's the slight manipulation of the last formula where we add on, they add on, we add on, they add on, as in the annuity problem. But this formula can be flipped around in one manner or not. And we'll look at that, explore that more in class. But if you were talking about in that annuity problem, when it comes time to cash that money out, well, then you're the one getting the payments while they're still paying interest on it. So this formula can be used for something that is in your favor. But we'll explore one of those in class in a couple of days. So that's it. These are some 4 examples of how to use geometric geometric and arithmetic series in some finance problems. I like this stuff a lot, really, really interesting. Hopefully you guys will kind of take some interest in this because, where you're going on in life now with all the money problems or money things that are going to be coming up, these formulas will come in handy. So hopefully y'all can retain these because I know I use these, unfortunately, regularly, way more often than I would like to. So that's it for applications to sequences of series, and I will see you in class tomorrow, guys.